Okay. Continuing with environment Shankar IS. Jai Jai Bhagwan, Jai Bhagwan Ji, Jai Mata Ji, Jai Bhagwan Ji, Jai Mata Ji, Jai Bhagwan Ji, Jai Bhagwan Ji, Jai Bhagwan Ji, Jai Mata Ji, Jai Bhagwan Ji, Jai Bhagwan Ji, Jai Mata Ji. Right. So continuing with the environment Shankar IS, let's see. What did we study? Yeah, POD, COD, then what plastics, right? Pollution index, EIA. So this was the last thing that we studied. 2022 amendments to the EIA. Alright, let's continue. So now we are studying the next unit, climate change. In this, let's see, chapter number of my 2018 edition book is chapter 19, ozone depletion. Right. So here we'll study about CFCs. CFCs, it is written 2/3 of the CFCs is used in refrigeration and 1/3 as foam. 1/3 as blowing agents in the foam insulation products. Right. Why CFCs are used? Well, they are non-corrosive, non-inflammable, low toxicity and chemical stability. So basically, they are ideal in so many senses. In commercial applications, therefore, they are used widely. They have non-corrosiveness, non-inflammable, low toxicity, chemical stability. Lifetime and removal. Just a second, let me see what is the problem. Lifetime and removal. So unlike other chemicals, mhm, the CFCs cannot be eliminated from the atmosphere by usual scavenging processes like photodissection, rainwater, and oxidation. Okay, so residence time of CFCs, right, is estimated to be 40 and 150 years. So during this period, they move upwards by random diffusion from the troposphere to the stratosphere. So their time period in the atmosphere is around 40 to 150 years, much more than the carbon dioxide. And during this time, it moves to stratosphere from troposphere. Right. Okay. Escape of CFCs. CFCs are thermally stable, as we just studied. They have all the ideal properties, right? They can survive in the troposphere, but in the stratosphere they're exposed to UV radiation. So CFCs, we just now saw, move to stratosphere gradually over the span of 40 to 150 years by random diffusion. Now in the stratosphere, they are exposed to UV radiation, right? UV in stratosphere. So what does UV rays do? They actually break down the CFCs. What is the breakdown product of CFC? That is chlorine, right? The full form of, because the full form of CFC is actually chlorofluorocarbons, right? So CFCs in the presence of chlorine, sorry, CFCs in the presence of UV radiation break down into chlorine atoms, right? Right. CFC, just a second. This is the equation, chlorine atom. This happens in stratosphere. Now, chlorine, here remember stratosphere has ozone, so chlorine combines with ozone to form chlorine monoxide plus oxygen, right? Simple chemical reaction. Then the ClO again combines with chlorine monoxide. Sorry, with just I don't know what is the error. Why is it interrupting my presentation? Anyway, so chlorine monoxide plus monoxide combines to form chlorine and oxygen. So again, chlorine is released as a product, right? free product. I mean, no association with any other molecule, any other atom. ClO plus O, they form this. This is the problematic thing, chlorine. Why? Chlorine is highly reactive. So we saw CFCs, they were very stable actually, and they were non-inflammatory, non-reactive, non-corrosive, low toxicity, chemical stability. However, chlorine is reactive. Now the depletion of ozone is cataclysmic, right? The element that destroys ozone is chlorine. So now, just now we saw chlorine is the main culprit. So what it does, it subsequently depletes ozone in the stratosphere, and it is being formed again and again, right? We saw now, chlorine plus ozone gives chlorine monoxide plus oxygen, and then chlorine monoxide reacts with monoxide to form uh, chlorine plus oxygen. So chlorine is generated again and again. Meanwhile, ozone is getting depleted. This was the reactions, right? 1 and 2, right? So chlorine is being regenerated while ozone is being depleted, right? This is the problem. So a single chlorine atom like this can destroy thousands of ozone molecules before encountering reactive nitrogen or hydrogen compounds, eventually return chlorine to its reservoirs. This is a chain reaction sort of thing. It will continue to happen until and unless chlorine encounters a compound which is more reactive than itself. So until and unless chlorine encounters nitrogen or hydrogen compound, reactive nitrogen hydrogen compound, it keeps on happening. So, but however, when it does encounter them, it returns to the reservoirs. To returns to its reservoirs. The chlorine does, right? This marks the end of this chain reaction. So this is the role of CFC. So therefore CFC is harmful or dangerous for the ozone, right? We just now saw the mechanism. Now let's see next is nitrogen oxides. Okay, before that, random fact: barking deer or common muntjac is the mammal with the lowest recorded chromosome number. Gives calls similar to barking, usually on sensing operators. It is least threatened. Alright. So least chromosome number is in a mammal called the muntjac, common muntjac or barking deer, right? Barking because it barks. Calls similar to barking. Then next, ozone depletion. Next thing that point where we're going to see is nitrogen oxides, right? So nitrogen oxide encompasses many compounds, many molecules like NO, N2O. N2O is nitrous oxide, nitrogen dioxide, NO2, right? Right. Sources of nitrogen oxides: basically explosions of thermonuclear weapons, industrial emissions, agriculture and fertilizers. So agri, then industries and thermonuclear weapons, right? Chemical reaction. Now let's see the chemical reaction associated with nitrogen oxides, thermonuclear weapons. All right. Chemical reaction is so nitric oxide. Okay, NO is also there. Yeah, we already wrote that. Yeah. Now nitric oxide, it is NO, reacts with ozone in the stratosphere to form nitrogen dioxide plus oxygen. This nitrogen dioxide reacts with nitrogen monoxide or nitrous oxide to form again nitric oxide plus ozone. So you see again, nitric oxide is regenerated at the end of the reaction, but in the process ozone is getting depleted, right? Now this nitrous oxide, what happens to this? So nitrous oxide is released from soil through denitrification. When we were studying the nitrogen cycle, we saw this. So nitrous oxide is released from the soil by denitrification by the denitrifying bacteria, namely Pseudomonas, I think was there, under anaerobic conditions, right? And nitrification of ammonia under aerobic conditions. So basically there are two mechanisms of escape of nitrous oxide. One is from nitrate. Let me write another page. For N2O, just a second. N2O, two methods. One is nitrate undergoes denitrification. Now this denitrification happens due to denitrifying material and anaerobic conditions. Right. So this region, this forms nitrous oxide. Second method is ammonium or ammonia undergoes nitrification. Ammonia undergoes nitrification. This happens under aerobic conditions and forms N2O, nitrous oxide. These are the two methods of escape of nitrous oxide. Let me see the nitrogen cycle again and we'll get somewhat more clarity. Where did I study the nitrogen cycle? Just a second. Yes, page 16 of this 2018 edition, right? So here, see nitrate undergoing denitrification, forming nitrogen. This nitrogen is actually in the form of nitrous oxide. Secondly, ammonia, or here ammonium, undergoes nitrification to form nitrate. Okay, so basically in the nitrogen cycle it is shown that ammonium actually forms nitrate by nitrification, and then subsequently nitrate undergoes denitrification, right? But yeah, directly we have seen here this thing. So this nitrification happens in aerobic, denitrification happens in anaerobic condition, right? Just remember this much, and that's how nitrous oxide escapes, right? This nitrous oxide, this nitrous oxide can gradually reach the middle of the stratosphere, where it is photolytically destroyed to yield nitric oxide, which in turn destroys ozone. Now see this. So this nitric oxide, this nitrous oxide reaches the middle of the stratosphere, where it is photolytically destroyed by UV radiation to yield nitric oxide. Yields nitric oxide, and this it comes here and it destroys ozone. So this is the chain reaction in case of nitrogen oxides, right? This is about this. Also, please remember as a side note, very important actually, not just a side note, nitrous oxide N2O is a greenhouse gas. However, nitric oxide is the real ozone depleting substance. So please remember this difference. Nitrous oxide is not an ozone depleting gas, right? At least not directly, so it is not counted as ODS. Alright. Next, other substances, bromine containing compounds like halones and HBFCs. It is hydrobromofluorocarbons, right? Both are used in fire extinguisher. Methyl bromide widely used pesticides. Now, bromine also destroys ozone, but what it does is, bromine, let's draw a line here. Bromine is more effective, more potent than chlorine in destroying ozone. So it destroys many more particles of ozone than chlorine, right? So it's more destructive. Next is sulfuric acid particles. These H2SO4 particles, they actually free chlorine from molecular reservoirs, convert reactive material into inert forms. So therefore we prevent the formation of chlorine reservoirs. Remember we studied just now before this topic of nitrogen oxides, that the only way that chlorine stops destroying ozone is when it reacts with reactive nitrogen or hydrogen, right? And it returns to its reservoirs. But what happens if this doesn't happen? So that H2SO4 particles or sulfuric acid particles prevent this reaction, prevent the chlorine to return to its reservoirs. Therefore, chlorine keeps attacking ozone, keeps destroying ozone. This is the role of H2SO4 particles, right? Okay. Then carbon tetrachloride, CCl4, and methyl chloroform, which is used as a cleaning solvent for clothes and metals, and a propellant in a wide range of consumer products, right? So what about those? I don't know. Just written here. Monitoring the ozone layer, well, it is a responsibility of WMO, WWW, ICOS, GCOS, etc. Right. Moving on to the next topic. Role of polar. That was not important. Next topic. Role of polar stratospheric clouds in ozone depletion. So this is an important topic. PSCs, or polar stratospheric clouds. Now, how do they deplete ozone? Basically, let's start from the basics. There are three types of in the stratosphere. There are three types of clouds. There are nacreous clouds. That means which extend from 10 to 20 kilometers. They are called as mother of pearl clouds or glow with a seashell-like iridescence. So, stratosphere, stratospheric clouds. Three types: nacreous clouds, right? Mother of pearl clouds, right? They glow. So glow. Next we have is clouds containing nitric acid HNO3 instead of pure water. So instead of H2O we have HNO3. That is the second type of cloud in the stratosphere. Third is same chemical composition as nacreous clouds but form at a slower rate. So larger cloud, but since they form at a slower rate they have no iridescence. So without iridescence, I think it's somewhat like glow only should be there. So glow or iridescence. There are three types of stratospheric clouds that we see. Now the chlorine released by the breakdown of the CFCs exists initially as pure chlorine or chlorine monoxide that we saw. Even chlorine monoxide is also active chlorine and it is unstable. But these further react to form compounds chlorine nitrate and HCl that are stable. What this means is stability means non-reactive. So chlorine, the same point, chlorine reacts with nitrogen oxides or whatever nitrogen compounds and hydrogen compounds, and it forms inactive or stable chlorine, right? N or H, stable chlorine, which is good for ozone, right? So it forms inactive chlorine. This exists in the form of HCl, right, or chlorine nitrate, somewhat like this. Chlorine nitrate, right? Okay. Now these are reservoirs of chlorine, so therefore they are inactive or stable. So no ozone depletion occurs subsequently. But now comes the role of the PSCs, the polar stratospheric clouds. Right, let us see. So chlorine is converted from its inactive to active state by the help of PSCs. How? The ice particles of the PSCs provide substrates for chemical reactions which free chlorine from its reservoir. Usually the reaction between HCl and ClO2 is very slow, but this reaction occurs at a faster rate in the presence of a suitable substrate which is provided by the stratospheric clouds at the poles. Right? So what this means is ClO2, HCl, here PSCs, they provide some sort of substrate, right? Provide, this is not PSL but this is PSC. Provide substrate. This substrate quickens the reaction of chlorine oxide or chlorine nitric oxide or HCl to convert into active fluorine. So active fluorine. This reaction is fastened because of the help of the substrate, which is provided by the polar stratospheric clouds. Right. Now, once chlorine is freed in its atomic form, we have already seen what happens. Right. It is just destructive for ozone. So here. So this is the reaction. So this is the role of polar stratospheric clouds. The molecular chlorine is formed and can be broken into atomic chlorine. Right. So this is one role of polar stratospheric cloud. What else? So they not only activate chlorine, but they also absorb reactive nitrogen. So not only are they expediting the reaction of inactive chlorine to active chlorine, but they also absorb reactive nitrogen. Now one may ask, what is the role of this? So basically, like I said, reactive nitrogen is required to put chlorine back into its inactive form. So once you take that thing, then again chlorine will not be inactive for a long time. So this is another problem. So basically it has twin effects, both aiding in the feeding of chlorine, more chlorine, therefore indirectly aiding in ozone depletion. Right. Now, random fact: every spring a hole as big as the USA develops in the ozone layer over Antarctica on the South Pole, smaller hole over Arctic at the North Pole. Right. And ozone layer is getting thinner all over the planet. Okay. Now, why is ozone depletion predominant Antarctic more than the Arctic? Why South Pole? Reason is Antarctic stratosphere is much colder, and since it is much colder, low temperature enables the formation of PSCs below 20 kilometers. So basically, the significance of PSCs in ozone depletion comes to be noticed when we see that the effect of ozone depletion is more felt in the South Pole and the North Pole. Right? PSCs are the major reason for that. Okay, now what happens is after once ozone is depleted, ozone depleted, it results in cooling of the temperature. Why? Because ozone actually absorbs the sunlight, right? What ozone does actually? Ozone shields us from the harmful UV radiation of the sun. Now, if ozone layer is depleted, more UV radiation would enter the earth. So, at the level of the ozone, the air becomes cooler. The troposphere will become warmer, but the air around ozone will become cooler. Now, once this air becomes cooler, further more PSCs are developed. So, you see, it's a sort of vicious cycle. PSCs formed. So PSCs form, again substrate will form, then again this, so again ozone will deplete. This happens. Right. Also, the formation of PSCs helps stabilizing the vortex. The vortex is a ring of rapidly circulating air that confines the ozone depletion in the Antarctic region. Right. But vortex is also formed or finds its favorable condition in the presence of PSCs. Vortex stabilize. Sorry. Right. So that is another problem with PSCs. Okay. The longevity of the Antarctic vortex is another factor, enhancing favorable conditions for depletion of ozone. The vortex remains in fact throughout the polar winter well into mid-spring, whereas the vortex in the Arctic disintegrates by the time the polar spring arrives. So this was one of the reasons the Antarctic stratosphere is colder, therefore more ozone depletion because of the formation of PSCs. Secondly, the vortex, it remains for a longer duration in the southern hemisphere than the northern hemisphere. Right? Typical happenings in the winter months leading to the ozone depletion of the Antarctic. In June, Antarctic winter begins. Vortex develops and temperature falls enough. During July and August, PSCs denitrify and dehydrate to the stratosphere, right, to free chlorine. September, sunlight reduces the height of the vortex. PSCs disappear. During October, lowest levels of ozone are reached. November, polar vortex breaks down. Ozone-rich air from the Mediterranean replenishes the stratosphere, and the ozone-poor air spreads to the southern hemisphere. Okay, so this whole ozone hole actually somewhat diminishes in November, right? But the lowest levels of ozone are reached in October. This was the mechanism. Now, next, about the Arctic ozone depletion. So, ozone depletion over the northern hemisphere has been increasing steadily. Apart from the buildup of ozone depleting chemicals, the main cause is the increasing cold temperature in the Arctic stratosphere, which again encourages the formation of PSCs. Okay. So, how ozone is measured? Dobson unit is the measurement of this unit of the thickness of ozone, I think, but there are many other. What is the Umheher technique? The Umheher technique. So remember just now I told you ozone is measured in Dobson units, which is the thickness of the ozone column measured at standard temperature and pressure in millicentimeters. In millicentimeters. So this is known as Umheher technique. So not much clarity is given. Just Dobson units is known as Umheher technique. This is measured in thickness of ozone is measured. Ozone thickness is measured in, very important, millicentimeters. Millicentimeters. So centimeter into 10 raised to the power millimeter is what? -3, probably, I don't know, millicentimeter. So 10 is to the power -5 meters, probably is the unit, probably. Let's see. How much is a millicentimeter? 0.1 centimeter. That is millimeter. See, millicentimeter. I don't know. Millimeter is what? Okay, whatever. It's not important. Just out of curiosity, I saw. But yeah, not much important. Not much given there. Okay, all right. Moving on. Ozone depletion. Okay, UVB radiation is the major radiation that is prevented from reaching the Earth by ozone. So UVB is the most energetic component of sunlight reaching the Earth's surface, and it has profound effect on human and animal health. So we saw this. We know this as a doctor. I know melanoma, skin cancer, all these potential harmful effects of UVB. Now, what are the effects on air quality? Changes in the atmospheric concentration of the hydroxyl radical or OH radical may change the atmospheric lifetimes of climatically important gases like methane, safety substitutes. Increasing tropospheric reactivity could also lead to increased production of particulates. So due to ozone depletion, increased particulate matter in the atmosphere occurs generally, and gases like CH4, CFCs, they also increase duration in the atmosphere, right? Yeah. Okay, moving on. Effect of the materials, synthetic polymers, naturally occurring biopolymers, as well as some other materials adversely affected. Just this must be adversely. Actually, everything is adversely affected, right? Any increase in solar UVB content due to partial ozone depletion will therefore accelerate the photo radiation rate of the material, limiting their life outdoors. Alright. Now, a random fact: grey slender loris found in India and Sri Lanka. India also, I think, in Tamil Nadu, South India, maybe. This chapter is completed. Next chapter is mitigation strategies, chapter 21. Let's do it quickly. I'm very, very, very behind. For next projections, man. What the fuck? I'm very behind. Let's do this quickly.